Hello, everyone, and welcome to Statistically Speaking with Dr. El Bayoumi, where we turn numbers into knowledge. In this video, I will take you on a quick journey through statistics. Before we begin working with formulas, graphs, or software, it is important to understand what statistics really is and why it matters. Many people think of statistics as a collection of numbers or complicated calculations. In reality, statistics is a way of thinking, a systematic approach to learning from data and making decisions in situations where uncertainty exists. Every day we are surrounded by data. News reports cite percentages, medical studies claim effectiveness, companies analyze customer behavior, and governments rely on data to shape policy. The challenge is not the lack of data, but knowing how to evaluate it, interpret it correctly, and use it responsibly. That is precisely the role of statistics. In this course, you will learn how data are collected, how they are summarized, and how conclusions are drawn from them. More importantly, you will learn how to ask the right questions, recognize limitations in data, and distinguish between evidence and opinion. Statistics will help you become a more informed student, professional, and citizen. You do not need to be a mathematician to succeed in this course. Our focus will be on understanding concepts, interpreting results, and applying statistical reasoning to real-world problems. Calculations are tools, but thinking statistically is the true objective. Today's video will introduce the foundations of statistics, what it is as a scientific discipline, how it is used, the types of data and studies we encounter, and the general process of analyzing data. This framework will guide everything we do throughout the statistical analysis. With that, let us begin by answering a fundamental question: what is statistics and why is it considered a science? So, statistics is the science of making inferences about random phenomena using limited sample data. It encompasses mathematical statistics, which develops new inference methods requiring abstract mathematics, and applied statistics, which applies these methods to fields like economics, psychology, and public health. Statistics involves making inferences about random phenomena using limited samples. Mathematical statistics focuses on developing new inference methods requiring deep mathematical knowledge. Applied statistics uses these methods in fields like economics, psychology, and public health, adapting them to specific subject needs. Now, let's define biostatistics. Biostatistics is crucial in addressing medical and biological challenges by applying statistical methods. Standard methods may not suit all studies, prompting biostatisticians to develop new techniques. This ensures accurate analysis and interpretation of complex data, enhancing research outcomes in healthcare and biology. Let's consider an example about how blood pressure readings can vary between automatic devices and manual methods. For patient X, the automatic device showed 115 millimeters of mercury, peaking at 130 millimeters of mercury, while the manual cuff recorded 90 millimeters of mercury. This discrepancy raises questions about the comparability of these methods, prompting further investigation into their accuracy and reliability. We conducted a small-scale study to compare the accuracy of automatic and manual blood pressure measurement methods. The study aimed to determine if these methods yield comparable results, considering variations in readings. This investigation is crucial for understanding the reliability and accuracy of different blood pressure monitoring techniques in clinical settings. Our study involved comparing the accuracy of automatic and manual blood pressure measurement methods. We designed a small-scale study to evaluate the accuracy and reliability of these methods. The study's design included selecting appropriate machines and participants, determining the sequence of measurements, and capturing critical data for analysis. We will test 4 machines, each with 100 participants. Measurements will be taken manually and then automated, as simultaneous readings aren't feasible. Key data will be captured via questionnaires for method comparison. Data will be recorded in a format that facilitates computer entry, ensuring accuracy in computerized data. We tested 4 machines to assess quality comparability involving 100 participants per location. Measurement order was randomized using methods like coin flipping and random number tables to eliminate method-induced effects. This ensures unbiased data collection, crucial for accurate analysis. Key data captured includes age, sex, hypertension history, and body size. Each participant received a unique ID for data entry. Data was coded, entered twice for accuracy, and verified. Editing programs ensured the values were within range, with outliers manually checked to maintain data integrity. Data collection involves gathering critical variables like age, sex, and hypertension history. Data entry requires assigning unique IDs and using coding forms for accuracy. Data editing ensures computerized data accuracy by checking variable ranges and manually reviewing outliers. Data analysis will summarize findings using descriptive statistics, either numerically or graphically. Data from studies can be summarized using descriptive statistics, either numerically or graphically. Numerically, data can be tabulated or shown as a frequency distribution. Graphically, data is presented pictorially, offering a visual summary. The choice between numeric and graphic depends on the data distribution type, whether numerical or categorical, continuous or discrete. The choice between numeric and graphic descriptive statistics depends on data distribution. Continuous data, like blood pressure, uses means and standard deviations. Categorical data, such as sex, considers percentages for each gender. Understanding these distinctions is crucial for accurate data representation and analysis. In our study, we encountered missing data due to invalid machine readings, a common issue in biostatistics. Notably, locations C and D showed apparent differences in blood pressure readings between machine and manual measurements. This discrepancy highlights the importance of anticipating data gaps and measurement variations during the planning stage. Inferential statistics help determine if the 14 mm of mercury difference in blood pressure readings is genuine or due to chance. With a sample size of 98, we estimate the mean difference, but the true mean difference, denoted as D, remains unknown. Calculating the error in this estimate is crucial for accurate interpretation. Statistical inference allows us to infer population characteristics from a sample. We develop a probability model to assess the likelihood of observing a 14 mm Hg difference in blood pressure readings between two methods in a sample of 98 people. A small probability suggests a genuine difference between the methods. We employ the t-distribution-based probability model, revealing a probability of less than 1 in 1,000 for machines at locations C and D. This low probability confirms a significant difference between automatic and manual blood pressure measurement methods. Further data analysis utilized a statistical package, a suite of programs for data description and statistical testing. Common packages and software include R, Python, SAS, SPSS, Stata, Minitab, and Excel. These tools enhance the accuracy and efficiency of data analysis, crucial for deriving meaningful insights from complex datasets. The final step involves incorporating essential data from the analysis into the manuscript for publication. This ensures that the findings are accurately represented and accessible to the scientific community, enhancing the study's credibility and impact. If you found this video helpful, don't forget to like, subscribe, and click the bell to stay updated on all things data and statistics. Thanks for watching.